Here we see the general model of computation, which is we talk about the Turing machine. So far we have discussed FA and PDA we have discussed. Now consider the language, like if you have the language L is equal to AN, BN, CN, where N can be greater than or equal to 0. Okay. And if you are asked to construct the finite automaton for this language or PDA for this language, then what you can do? See, you have seen in case of the FA, you cannot construct the finite automaton for this language, as this is not the regular language. This is not a regular language, and also this is not a context-free language. So you can't remember, in case of the finite automaton, you can't remember the number of A's and number of B's. Once n is sufficiently large, then it is not possible for in the finite state machine to learn the sufficiently large length strings. So for the case of the FA, we cannot construct the machine. Finite automaton we can't construct for this language. Also, if you go for the PDA for this language, then you have seen that A and BN you can correctly match. Once you have the A, then you can push onto the stack, and once you start reading the B, you can delete one by one from the stack, and once you have the B exhaust and you see that the stack becomes empty, then this is the case that number of A's and number of B's you have matched. But see that how you can also match the same number of C. So number of A, number of B, and number of C you need to actually match. So here in case of PDA, one stack is not possible. If you go for the PDA, then you have to use the two stacks for this case. You need two stacks for this language. So in stack 1, you have the stack, okay, this is the stack 1 and this is the stack 2. So in stack 1, what you need to do? You have to save A's. You have to save A's. In stack B or in stack 2, you have to save B's, like this. Whenever you start reading C, you can delete the A's from the stack 1, and you same times you also delete the B from the stack 2. Once you go for the next C, again you delete one A from the stack 1 and B from the stack 2. Whenever you see exhaust, whenever you have read the C completely and you see that stack 1 and stack 2 both becomes empty. If both stack becomes empty, then you can say that, okay, yes, we have the number of A and number of B, and also we have the number of C. Same number of A, same number of B, and same number of C, and you can match. So instead of using only one stack, you have to use here two stacks. Now, if you consider the language like this, if you have the language, say you have the language S, where S is what? S belongs to AB clean star. So you have the SS and S belongs to AB clean star. So what you can do here what is that? The string has two parts. Like if you have the S, so you have S is equal to A double B. Then in this language you have the SS, which is A double B, A double B. So A double B, A double B. So you have the two part. In the first half you have the first S, and in the second half you have the S. Now see, even you can go for the PDA, you cannot construct the PDA for this language. Why it is so? Because once you push the first half onto the stack, then your stack top becomes B here. And once your stack top becomes B here, and you have to start reading A, and whenever you have A, you want to match this A with the bottom of the stack, which is A here actually. And how you can't, there is no way to access the bottom in case of the stack. You can access the top element of the stack. So even stack data structure is not suitable for this language. If you want to construct the models of computation for this language, then even stack is not a suitable data structure for this. In this case, what you need to take, you need to take queue. So you have the queue, you can queue as a data structure, which is the first in first out data structure. So you need, in this case, actually you need to store the elements in the queue. So whenever you are going to start reading the next part, you just access the element from the queue, because this is the first in first out. So first you have stored, which is A, and you have to match with this first symbol of the next hop. So here queue data structure is suitable for this language. And both two stack and using the queue as the data structure, both are the model of computations. Here we see Turing machine. So Turing machine, once you talk about the Turing machine, actually is invented. This is the abstract machine which is considered as the model of computation, and the mathematician Alan Turing during 1936 invented this machine. And in his paper Proceedings of the London Mathematics Society, and volume 2 and page number 232 265 during the year 1936. You can find the description in this paper. So during the 1936, Alan Turing has come up with an abstract machine that is considered as the model of computation. And actually, Alan Turing has thought about the human computer. So how human being is going to compute? So as a human being, human is computing working on the pencil and paper. So we have the pencil and paper. So actually we are going, say we have the papers here. We have the paper, okay. We have the pages like this, pages of the notebook, you can say. These are the pages, okay. And you can have many pages, okay. This is like this. You can have any number of pages like this. So say this is the page number, say for example 50, and this is the page number, maybe like this. Page number maybe, say it may has the 100. This may have the page number 150. This may be having the page number 200. So see, in the human being, we have the paper, and human being is working with pencil and paper, okay. So how actually human being is going to work? We are writing one symbol at a time, like we have written A, B, C. So one by one we are writing the symbols, and if you wish that, okay, yes, this is wrong, you can delete. So once you come to know that you have written wrong, then you can delete the symbol. So you can delete. So you can delete, and you can write some different symbol like B, and you can write like this A. So you can read the symbol. If you want to wish, you can erase the symbol, or you can change with some other symbols. So actually Turing machine has thought about the human computer. So we have the human computer. Means human is computing with pencil and paper. So just like we are working on the algorithmic way and we are writing the primitive steps in the sheet of papers, so we can write the symbols in the sheet of papers, and we can have multiple lines. You can write in this line, you can write any number of lines. Finally you can go for this, say CO, and you can write like this. Then from this page you can jump to the page number 100, and you see that what symbols are written here. You can see, you can change the symbol. From this page number 100 you can go to page number 150, and you see that okay, there may be some symbols you want to find the symbols, and you may, if you are interested, you can change the symbols with some different symbols. And you have, from this line, if you wish, you can go to the bottom of this lines, and you can see that what symbol is written at the bottom of the line. So human being is using the pencil and paper, and from one line human being, we can change, we can go to the different lines. From one page we can jump directly to the different pages, or you just open the page one by one. If you are at the 50, then you can go for the page number 51, then 52, 53, and if you wish, you can jump directly to the at the last of the page, or you can have any number of, you can skip any number of page at once. And you have the different states of mind every time. So every once in the human beings, we have different states of mind. At the beginning, we have some different state of mind. At the end of the input, we have some different state of mind. Like during the beginning of this course, theory of computation, you have some different state of mind. At the after 2-3 classes, you will have some information. On behalf of that, your state of mind is going to change. At the end of this class, your state of mind is further going to be changed. And unfortunately, in case of the human beings, we have infinite possible states of mind. So Turing machine actually has thought about the human computer, where we see that human is working with pencil and paper, writing the primitive steps of the algorithm on the piece of paper. And if we have the different states of mind, every time we can change our states of mind on behalf of the input. We read, we observe, or we can modify. We can jump from one place to the other place. We can work on two-dimensional sheet, and like this. So this is the human computer. However, we are using the Turing machine, which is the restricted version of the human computer. So instead of the sheet of papers, what we are having, we have the tape. So we have the tape, and you can say this is the tape we have. Okay, and we have the tape, and we assume that tape has sufficient capacity. We can store any amount of information like this. And for the simplicity, we can assume that the tape is of having the left end, and it can grow to the right side infinite. So you have the tape, we are using the notion, and you can say right side, possibly this can go to the infinite. Okay, and here we have the tape, and we can divide the tape into, we can square the tape into the squares. You have divided the tape into the squares, and exactly you will be able to write one symbol in every square. So tape is squared off. So you are writing the every one symbol in one square, and so on. So you have the tape, you can write just only one symbol, or the The square may not contain any symbol. When a square is not containing any symbol, we say that it is containing the blank. So if there is nothing, means it is the blank we have. So like this. So you have the squared like this. For simplicity, you can number. We are going to number the squares, and starting from the 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. You can number like this. So instead of the pencil and paper, we are having the tape. In case of we have the tape, and we consider that tape is of left-handed, and it can go into the right side infinite. We have squared of the tape, and we can number. For simplicity, we have number the tape squares starting from the 0. So tape may contain some symbols. Every square can contain only one symbol, or it may not contain any symbol. Then we will see that there is a blank symbol in the tape. Now this is one restriction where you can say instead of having the multiple line multi-dimensional, you have the one-dimensional tape here. And for this tape, we have one read-write head. So you have the tape head. Tape head, we have the tape head. Okay. So tape head can scan any square at one time. Means when tape head is positioned at the square 2, means it can read the symbol stored in the square 2, or also it can replace the symbol stored in the square 2 with some other symbol, or it can replace with blank, means it can delete it. Question is that just like in this case, if you are at the page number 50, human can jump from page number 50 to the page number 100 directly. But in this restricted version, what we are claiming that if you want to go from square 1 to, say for example, this may be the square number 200 or 2000, whatever. From square 1, if you want to go to the square number 2000, then direct jump is not possible. What you need to do, you just scan the squares one by one by making the moves of the tape head to one square at a time to the right. You can find the pattern stored at the square number 2000. So here tape head can be moved to the right, tape head can move to the left, one position left, or it may kept stationary, means remain in the same position. So we can move the tape head either to the left or either right, or we may wish to not move, and hence tape head can be kept stationary. But once it moves only one symbol, one square, either left side or right side. In direct jump is not possible, just like in case of the if condition. Okay, if you have the if condition, if something is true, like if you say that if A is greater than B, then you are doing some job, else you are doing some job. So you are jumping. So here this kind, in case of the Turing machine, how you can simulate this? This direct jump is not possible. What you can do, if you want to go to this place, say this is the place A and this is the place B. If you want to go to the pattern stored at the B, then what you need to do, you have to move the tape head one by one to the desired location until you are going to find the pattern. So direct jump is not possible here. You have to move the one square at a time. So this is one restriction. Means next restriction. First we have considered one-dimensional tape instead of two-dimensional sheet of paper. Next, we can move the tape head only one position to the left or to the right, or we cannot move. Direct jump is not possible. And see, in the human beings, we have the infinite states of mind. And what in the restricted version of this human computer, which we consider as the Turing machine. Turing machine is the restricted version we are using, where instead of infinite possible states of mind, we need only the finite states of mind. So for the case of Turing machine, we have the finite states. So we have the finite states of mind. In case of the Turing machine, we have the tape as one-dimensional storage, and we have the tape head which can read and write the symbols on the square on the tape. Tape head can be moved only one position, either left, right, or it can be kept stationary. So this is the restriction in the Turing machine, and this is the basic Turing machine. Although in the next class we will see that there are a lot of variations of this Turing machine, and the intuition of the variations are what? The only intuition is to simulate the human computer. We need to simulate the human computer by going through the variations. So somebody may think that okay, instead of having only one tape, we can tape the multiple. You can use more than one tape. So once you go for the more than one tape, okay, so you have the one tape number 1, then you can go for the tape number 2. Like this, you have the multiple tapes. So in the variations, we will see that instead of having only one tape, we can keep also multiple tapes. Okay, with the intuition that we have the two-dimensional sheet and two-dimensional sheet, we can work. Human being can work on the two-dimensional sheet of paper, and for simulating the human computer, you may increase the number of tapes, and also instead of making the tape left hand, you can grow in both sides infinite. So whatever variations we are going to obtain, or whatever variations we have for the case of the Turing machine, this basic machine is much powerful, as at least as powerful as you have the variations. Means whatever variations you can go, the same job you can also perform with the help of the one-tape Turing machine that you can perform in the multi-tape Turing machine. So even in the basic version of this Turing machine is much powerful. So we have the Turing machine, which we are using the restricted version, and this is the machine which we can say this is the model of computations, and modern computer is actually the Turing complete. So we can perform every action that whatever job you can do with the help of your computer, you can also do with the help of your Turing machine. If you can do some task using your computer, there is some Turing machine can also do the same task. So till now, what we can say that this Turing machine is much powerful, and any computation, if you can perform with the help of your computer or with the help of the group of person or a team of person, the same you can also achieve with the help of the Turing machine. And you can say, so what you are seeing that any algorithmic procedure that can be carried out by a human, a team of humans, or a computer can be carried out by some Turing machine. Means whatever you can do, or whatever a team of persons can do, whatever the job can be performed by some machine, the same we can also perform with the help of Turing machine. Means Turing machine is much powerful, and this is the one general model of computation, and this is one of the powerful model of computation. There is no powerful model exist after the Turing machine, and this is the statement first mentioned by the Alan Church. So Alan Church has mentioned this statement. Alan Church during 1930s. So during 1936, Alonzo Church has mentioned the statement like this: what is any algorithmic procedure that can be carried out by a human being, a team of humans, or a computer can be carried out by some Turing machines. Means over Turing machine was invented during 1936. Okay, and we have over 80 years have been passed. Over 80 years have been passed, and even we have not encountered any experience. We don't have any experience for which we can say that this statement is wrong. Means if we can do, or a team of person can do, or some machines can do, the same problem can also be solved with the help of Turing machine. We can't say that okay, we can solve this problem, but Turing machine is not able to solve the problem. We have no such experience. Even more than 80 years have been passed, and this is the statement given by the Alonzo Church during 1930s in the paper in the paper which is published in the American Journal of Mathematics. So you can go to this paper for more description. So this statement given by the Alonzo Church, and this is popularly known as the Church-Turing Thesis. So you can say this is the Church-Turing Thesis. So what this Church-Turing Thesis says? This is Church-Turing Thesis. This is the Church-Turing. So this thesis actually explains that the Turing machine is much powerful model, and even we can compute any functions with the help of the Turing machine that can be computed by a human, by a team of humans, or by some computer. If functions can be computed by a human, or if function can be computed by the team of persons, a group, or if function is computed by some machine, then the same function we can also compute with the help of Turing machine. In fact, if you are not able to compute, if some team is not able to compute, if a human being is not able to compute, or some computer is not able to compute, then we can also not compute with the help of Turing machine. But whatever you can compute with the help of computer, or people with a group can solve the problems, or a human being can solve the problem, the same problem if you can solve, then Turing machine can also solve the same problem. So this statement is given by the Alonzo Church, and even this statement is not proved mathematically, as the definition for the algorithmic procedure is not precise, and hence there is no way to prove it mathematically. But even over 80 years have been passed, we could not find any instance where we can say that we can solve the problem, but the same problem cannot be solved by the Turing machine. So if you can solve the problem, we will have some Turing machine that can also solve the problems. So Turing machine is much powerful model of computation. Still, we have over 80 years have been passed, and there is no more powerful model exist after the Turing machine. Okay. So once you go for the Turing machine, what we have? Turing machine now makes the decisions. Turing machine has now finite number of states. Okay, the number of states in the machine is finite, and Turing machine can write the symbols one by one symbols in every square. Okay, or it can replace the existing symbol with some other symbol, or it can delete. Okay, so you can write the symbols on the squares of the tape, you can delete. So tape head is there, and tape head is reading the sum square. Tape head is positioned the center of some square. In fact, it can read the symbol stored on the square. So Turing machine is now made this decision on the basis of what? On the basis of the current state of mind, and the current symbol is scanned by the head, current symbol that is read by the head. So on behalf of the symbol, tape symbol, it is going to read, and on behalf of the state of mind, its state of mind, it is going to make the decision. And what it can do? Your Turing machine can halt by saying that yes, computation is over, or Turing machine can go from one state of mind to the other state of mind, means it can change the state, or Turing machine can also move the tape head to the left side or to the right side, or Turing machine may not move the tape head either left or right, and it may keep the stationary. So on behalf of the current state of mind, on behalf of the tape symbols, it can make the decisions, and it can go to the next state, it can transit the state, it can move the tape head to the left or right, or it can keep stationary, and also it can modify the tape symbol. So three actions have been performed. Three action is going to perform: transit the state, okay, state transition, or replacing the symbols, tape symbols, or you can move the tape head. So there are three actions you can perform with the help of on behalf of the current state of mind and tape symbol. Here, once you talk about the tape, this in case of the Turing machine, we have given tape as the storage. So you can go from this end to any other part of this tape, and again you can come back to this, means you can repeat. Your tape head can go backward and forward. There is no restriction. Any number of times you can move either right side or left side, anyway. Okay. So here at the beginning, we can store the input onto the tape. The tape is also acting as the input device. So this is also, tape is also the input device for the Turing machine. So at the beginning, the input is stored onto the tape, and hence tape is also acting as the input device. Once computation is over, then whatever output is there, we can, the output is stored, whatever left onto the tape, that is the output after the computation. And in this case, you can say that after once computation is over, then whatever is output is there, it is stored onto the tape. So tape is also acting as the output device. So your output is also stored on the tape. During the computation, you are also using the storage, tape storage, as the doing the rough work and for intermediate computation. So tape can also be used as the rough work or doing the intermediate computation. So tape is acting for the three purpose. One is for the input purpose, means at the beginning your input will be stored onto the tape. Once computation is over, whatever is left after the computation, that is stored on the tape, and hence tape is acting as the output device also. And during intermediate computation, you can use the tape just like the doing the rough work. So you can have the three purpose for using the tapes here. So actually sigma behaves sigma, whatever be the input behave, input alphabet, the input is stored onto the tape, and hence input, every symbol that are in sigma can be stored onto the tape. And besides this input symbol, you can also, for doing the rough work, for intermediate computation, you can use some extra symbol that can also stored onto the tape. Here we see the formal definition of your Turing machine. Turing machine, TM is a 5 tuple, Q, sigma, tau, Q0, delta. And Q is, as usual, Q is what? Q is finite set of states, okay, assumed to not contain the halt states, HA and HR. Okay. So what we are assuming that Q is the finite set of states, and we have two additional states which we denote by writing HA and HR. So assumption is that HA and HR does not belong to Q. This is important thing. So we have the two states, extra state, one is HA and HR. So we will use the HA and HR for denoting the halt state. In this case, what we have, Q is the finite set of states, and what we are assuming that HA and HR is not in the set Q. We will use HA and HR for denoting the halt state. HA is the acceptance condition and HR means rejection. So once your Turing machine decides that this is the case of acceptance, your Turing machine goes to the halt state and stops. Once it decides explicitly that the computation is not done correctly, and this is the situation, it means Turing machine explicitly thinks that it is the situation of crash. So it rejection, so it goes to the HR state, means rejection. So these two states are not in the set Q. In sigma and tau, this is the alphabet of input symbol and tau is the alphabet of tape symbol. So we have also already mentioned that at the beginning your input is stored onto the tape, and hence sigma with condition that sigma is the subset of tau. Whatever input symbols are there in the sigma, these are also the tape symbol, and beside these symbols you can use some extra symbols also. We also assume blank symbol is not a tape symbol. So black symbol is not in the tape symbol. So tape symbol does not contain the blank symbol. So when there is nothing in the square, we assume that there is a blank, and blank symbol is not the tape symbol. Q0 is what? Q0 is initial state of the machine. Your Turing machine starts with the state Q0, and this is an element of Q. Now we have the notion of the transition function. So for the case of Turing machine, we are going to define the transition function delta. So transition function delta is defined like this. You are in any states of the Turing machine. You are observing, your tape head is observing any symbol from the tau union blank. Okay, so any symbol, and on behalf of this, it can go to the any state of the Q union HA HR. Okay, so from the state Q, you can go to the state any one element of the Q, or your machine decides that okay, this is the case of acceptance, it can go to the HA, or it can also go to the, if it decides that okay, this is the case of rejection, it can go to the state HR. Next, it can modify the tape symbol tau union blank. So it can write the tape symbol in the square. You can write any tape symbol, or it can delete with the by replacing with the blank. Then you can move the tape head to the left side, to the right side, or you may not move the tape head. You may keep stationary. And this transition function is a partial function. This is a partial function. This is a partial function. And what do you mean by the partial function? That is, it may not be defined at certain point. certain point. So delta is the transition function. Delta is actually the partial function. Why it is partial? Because there are some situations where you cannot define. Like we have seen that you have the tape, and in the tape we have the notion that this is the left-handed tape, okay, and this is the square 0, and this is the square 1. Whenever you are having the tape head, okay, and it is the scanning the square, say 0, and once you are at the position 0 and you say that, okay, you move to the left, then left move at this position is not possible, because moving the tape head left, this is not done here, because tape head is already at the left end, and hence the function is not defined. The left move is not defined once your tape head is at the square 0. So this is one of the example where you can say that the transition function is not defined for the left move once your tape head is scaling the square 0. So this is the condition. So what you have seen that the Turing machine is a 5 tuple, just like, okay, we have the other machines. It is a 5 tuple, and what are the contents in the 5 tuple? You have the state, you have the 5 things. One is the Q, which is the set, which is the states of your machine, means state of mind. And this is the input symbol, tape symbol, initial state, and transition function. Input symbols are also the tape symbol, means sigma is the subset of tau. Tau does not contain the blank symbol. Q is a finite set, and it is not containing the two state HA and HR, which are the halt state. Okay, Q0 initial state, which is from the Q, and this transition function of the machine is the partial function. So how you can, this transition function, you can say, you can define using the diagram like this, or say if you are at the state Q and you have the input, say you have the X. X can be what? You can have the X which belongs to tau union blank. So X can be either any symbol from the tape or it can be blank. So your current state, you are in the Q, and the tape symbol is either any one symbol or blank. And your output is what? Your output is triple. What is triple? One is state, other one is the tape symbol or blank, and last one is the direction. So here you have the state. You say you are going to the state R, and you are modifying the tape symbol, and you may replace with Y, and you are moving the tape head either left, right, or stationary. So here X is any symbol from the tape or blank. Similarly, Y is also any symbol from the tape or blank. R is what? Q can be any. Q belongs, okay, Q belongs to Q. Okay, Q belongs to Q. Where R can be, R is what? R can be anything. R can belongs to either Q, or R can be HA, or R can be HR. Means your machine can transit from Q to R, and R can be halt state. Once machine decides, then it can transit to the halt state. And D is what? D can be anything, either left side or right side, or you are not moving the tape head and you are keeping the stationary by writing the S. In transition diagram, with the help of the transition diagram, you can show like this. So this is, you are at the state Q and you are moving to the state R, and for what? For the case of tape symbol is X, and this tape symbol is replaced with Y, and you are moving to the tape 8. And D can be anything, either left, right, or S. So this is the way you can denote with the help of the transition diagram. Here we have mentioned that once your machine starts, At the beginning, at the beginning, the input is stored onto the tape, and for our notion, at the square 0, we have the blank symbol. Okay, and tape head is scanning the currently tape head is scanning the symbol this blank, and immediately after the square 0, you have the input. Your input is stored immediately after the blank symbol 0. So from here you are going to store the input x, and after the x everything is blank. X does not contains the blank symbol because this is x is taken from the sigma. X is any string from the sigma, and x does not contain the blank symbol because blank is not a member of sigma. So x does not contain the any blank symbol. So what you have your input at the beginning. Your input is stored from the square 1, and immediately after the x you have everything. Say if you have stored the input up to this point, then immediately after this x we have the blank symbol. If there is nothing, we have the blank symbols. So this is the situation at the beginning. Means you can say that machine at the beginning, your machine is at the state q0, and the situation of the tape is like this, and you have the x. What it says, this is the configuration. Actually, this is the configuration of a TM. This is configuration. What this configuration shows? So your configuration is a pair. First one is what? This is the current state. So you are having the current state. So when you talk about the configuration, then we are talking about the pair actually. So configuration of TM is a pair. Say you are having Q and Q X A Y. Say if you say this is the configuration of TM. So configuration of a TM is denoted by writing the pair Q X A Y and like this. So Q is what? This is the current state. This is the current state, and X A Y, X and Y can be any string. X and Y can belong any string from the tau union blank. Any string that consists of any symbol from the tape or blank. So this is, and the first leftmost symbol of the X is stored at the square number 0. And I am underlining this symbol. This means currently your tape head is scanning the symbol A. Y is also the string from the tau union blank, but if Y is null, then after A you have the blank symbol only, and if Y is there, then the last symbol of the Y must not be blank. So this is the last symbol should be non-blank. So everything after this Y is blank. So this configuration says that your machine, your Turing machine, is at the state Q, and currently this is the contents of your tape. So starting from the square 0. So I am underlining this, and if you have the situation, if you say like this, if you have the Q and X, W, Y, and I am underlining W, where length of W is greater than 1. If length of W is greater than 1, then, and if you are going to underline this, this means what? This means your tape head is scanning the first leftmost symbol of this W. So this is, so at the beginning, once you see the configuration of the machine, Turing machine, then at the beginning you have only input onto the tape, and square 0 contains the blank symbol, and your tape head is scanning the square 0, and immediately after this blank is you have the input, and everything after the x is blank, but we don't require to mention the blank. Okay, everything after the x is blank. So this is what? This is the initial configuration. This is initial configuration. Why it is initial? Because your machine starts with the q0 and you are given the input x, and x belongs to sigma star. So when x belongs to the sigma star and your current state of your machine is q0 and your head is scanning the symbol blank symbol at the square 0, this is the initial configuration, and your machine starts with this initial configuration, and by making sequence of moves it can go to some different configuration, like it can go to the configuration say r, x, y, and z. Okay, so your machine can go to this configuration, anything. You can have the y maybe length more than 1, or you just have the symbol, say for example a. So here r can be what? R belongs to, r can be any one element of the q, or r can be either ha or r can be hr. Your machine, by making the sequence starting from the initial configuration, your machine, there is a way to reach this configuration. And what this configuration says, this says that r is some state, r can be any one element from the q, or r can be ha or r can be hr. Means machine can go to the, once r is equal to ha, this is the case of acceptance. Once r is equal to hr, this is the case of rejection. Okay. And x is z, this is the current content of your tape. So x leftmost symbol of this x is at the square 0, and x and z is what? X, z are the string which is taken from the tau union blank. This is the string from the tau union blank. A belongs to either tape symbol, or A can be blank. Underline shows that your tape is currently scanning the symbol A. So this is starting from this initial configuration, you may go to some configuration, intermediate. And from this configuration, by making the sequential move or one move, you are going to some different configuration, say R1 like this. So if your machine start from the initial configuration, and if you have the situation that your machine goes to the state HA, if your machine is going to the state HA, starting from the initial configuration, while taking the input X, your machine, by making the sequence of machine in the Turing machine, there is a way to reach the halt state, which is the acceptance state, and whatever be the contents of the tape here. If you are using, if you have constructed the Turing machine as a language acceptor, so once your Turing machine decides that okay, the given input is in the language, it goes to the halt state HA. Okay, and then whatever string you have stored onto the tape, it doesn't matter actually, because what is the importance here? Your machine has decided that okay, the given input is in the, your given input is in the language, and this is the current contents of the tape. We are not bothering. Our aim was to whether make the decision whether the input is in the language or not, and your machine has made the decision. Once you are computing some partial function, then this thing, contents of your stack is tape is important, because this is just like the output. So whenever you are computing the partial function, say q0, and for the parameter x, And by making the sequence of moves, your Turing machine, in the Turing machine, and your Turing machine goes to HA, means computation is done successfully, and then you will have the situation like this, fx. So this may be the situation. This shows what? You are starting from the initial configuration while taking the input x, and you are computing the partial function. And by making the sequence of moves in the Turing machine, there is a way to reach to the HA, means after computation, there is a way to do the computation and successful computation, because your machine goes to the HA, and whatever is, this is the contents of your tape, whatever is contents of the tape, this is the output of your partial function, so fx. So your Turing machine is not only acting as the language acceptor, it can compute any partial function. Okay. So in this way you can say, so here the language accepted by the Turing machine is denoted by the set, by writing LT, the language accepted by the Turing machine. This is what? This is the set of x, which set of x taken from the sigma star, such that x is accepted. So it is the set of x from the sigma star such that starting from the initial configuration, assuming that we have the t here, and t is q sigma tau q0 and delta. This is the t, and means q0 is the initial state. So the language accepted by the Turing machine T is given by the set of x, which is taken from the sigma star, such that starting from the initial configuration, this is the initial configuration, and by making the sequence of moves in the T, your machine goes to the halt state HA, and YAZ. This is the output. And YAZ, HA is the halt state, and say YAZ, it goes to the halt state. This means starting from the initial configuration, there is a way machine has decided that, okay, yes, this is in the language, this X is in the language, and hence it goes to the HA. So for all such string for which your machine starts from the initial state, initial configuration, and it goes to the final configuration, all such strings are in the language of Turing machine. So LT, language accepted by the Turing machine, is precisely the set of strings for which your Turing machine starts from the initial configuration and it goes to the final configuration. This is the final configuration. Y and Z are the strings from the tau union blank. Any strings from the tau union blank, and A is some symbol from the tau, or it can be blank. So this is the way you can say that X is accepted by the language. Okay. Now here you have the situation. We are using a tape. Okay, we have the tape, and in this discussion, in this restriction, we have tapped and the tape. Okay, I'm making the squared tape is squared off. Okay, tape is squared out, and you are numbering the square for simplicity. Okay, like this. So here, in case of the Turing machine, when you go for the Turing machine, for the case of Turing machine, we have the situations. What situations? Turing machine halts. Turing machine halts at HA, or Turing machine halts at the state HR, or it doesn't not. Means Turing machines may loop forever. Turing machines loops forever. Forever. So these are the three situations with the Turing machine. In case of the FA or PDA, we have only two situations, either the case of rejection or acceptance. So here, if Turing machine goes to the state HA, if it goes to the state HA, this means Turing machine has decided that is yes, computation is successfully done, and this is the case of acceptance. Once Turing machine decides that okay, this is the case of explicitly decide that this is the case of rejection, and hence it halts in the state HR. If like if you are designing the Turing machine, constructing the Turing machine as a language acceptor, then if Turing machine comes to know that the given input is not in the language, then Turing machine halts in the HR state. Means R means you can simply mean that rejection. And if Turing machine decides that okay, yes, given input is in the language, then it goes to the HA state. There may be, for the case of the Turing machine, there may be the situation that Turing machine for some input, Turing machine may not be able to decide in some reasonable time whether it is in the language or the input is not in the language. Turing machine may loops forever. Once Turing machine may loops forever, then this is the undecidable problem. This will become the undecidable problem, which means you cannot decide whether the given input is in the language or not. If for the given input x, Turing machine enters to the infinite loop, it loops forever, means it is unable to decide whether x is in the language or x is not in the language. And this is the situation when we can say this is the undecidability, and we are not going to decide. Turing machine is not able to decide whether x is in the language or it is not in the language, because there is a possibility in case of Turing machine to loops forever. As you see that there are infinite the tape is infinite in the right side. It may loops forever for some input. So in case of Turing machine, we have the three situations. One is Turing machine explicitly decides that okay, yes, it is in the language, or computation is over successfully, and I have to go to the HE state. Or Turing machine explicitly decides that okay, this is the case of clear-cut case of rejection, and hence Turing machine goes to the HR state. Or Turing machine, it may be possible that for some input, Turing machine is not going to stop. It loops forever. Once it loops forever, then we can't say that whether the input is in the language or not, because we don't know at what time Turing machine is able to make the decision. So this is the undecidable. This kind of thing is undecidable. So there is also the third possibility in case of the Turing machine for the loops forever. And once Turing machine is loops forever, then undecidability comes. We are not able to decide for the input whether it is in the language or it is not in the language. So this is the situation of the Turing machine. That's why the language accepted by the Turing machine is what? The language accepted by the Turing machine is the set of string x for which Turing machine halts in HA. Means Turing machine explicitly decides that yes, this is in the language. So the all strings for which Turing machine explicitly decides that this is in the language, then they are in the, this is in the, and we can say that this is the language which is accepted by the Turing machine. So language accepted by the Turing machine is the set of string x for which Turing machine starts from the initial configuration and it goes to the HA, halting configurations, or means final configuration in the state H. Okay. So this is actually, we have seen the sufficient background, sufficient basics about the Turing machine, and in the next classes We will see some examples, and you will see that how you can construct the Turing machine, and then you will come to know the power of Turing machine, the problems for which you don't have the FA or you don't have the PDA, but you have the Turing machine. So you will see that in the coming lectures we will discuss. You will come to know some problems which can also be not solved with the help of Turing machine. And if you are not able to solve with the help of Turing machine, it means your modern computer is also not able to solve, because your modern computer is Turing complete. Whatever job you can perform with your computer, the same you can also perform with the help of one tip Turing machine. Even. So your computer is Turing, modern computer is Turing complete, means if you are unable to solve the problem with the help of computer, this means there is no Turing machine to solve that problem. Okay.